It's like a jungle sometimes, it makes me wonder how I keep from going under. It's like a jungle sometimes, it makes me wonder how I keep from going under.
We're in the process of proving that for any field f, there exists an algebraic closure of f. And we've already said where this algebraic closure is going to come from. It's going to be a quotient of a giant polynomial ring. So this polynomial ring is called A, is going to be the polynomial ring generated over f by these variables tfi. So where do these come from? For each monic non-constant polynomial f, say it has degree nf, we get nf of these variables tf1 up through tfnf. And what is this quotient that we're going to take of this giant polynomial ring? Well, we're going to find the ideal that we're quotienting by, starting from this ideal I, where I is going to be the ideal of A generated by all of the coefficients of a huge number of special elements in A bracket x. What are these special elements? For each non-constant monic polynomial f of x, we're going to take the element in A bracket x, which is f of x minus the product of x minus tfi, where we go over the set of variables corresponding to this monic polynomial f. Okay, so where are we going to go from here? Well, we've seen that some polynomials that we care about factor nicely in A mod I bracket x, but we don't know anything really about A mod I. In particular, we don't know if it's a field or not, because we don't know if I is a maximal ideal. So the idea here is that we want to show at least that I is a proper ideal, because then we can apply Zorn's lemma and say that I is contained in a maximal ideal. So we've proven that if you have a proper ideal, it's contained in a maximal ideal. This was an application of Zorn's lemma that we saw when we first discussed ideals in rings. So then I is going to be contained in a maximal ideal M, and A mod M is a field. So in fact, we're going to show that A mod M is an algebraic closure of F, but this is another big part of the proof. So in the short term, what do we need to do? We need to show that I is a proper ideal of A, that 1 is not an I. All right, so what are we going to do? We're going to suppose that 1 is an I. And what does that mean? We're going to find a contradiction here, but what does it mean for 1 to be an I? Well, I is an ideal generated by a set. So what do elements of I look like? They're finite sums of something in A, in this ring A that it's an ideal of, times something in this set. So what we get is there exists A1 up through AM in A such that A1 times C1 plus 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 AM times CM equals 1, where these CJs are things from this set. They are coefficients of elements that look like this. So each CJ is a coefficient in some difference Fj of x minus, oh, this should be a product. You can pretend I made that mistake on purpose to check if you were paying attention. Fj of x minus the product from I equals 1 to nfj of x minus tfj comma I, where, okay, what is this fj of x? This is some monic polynomial of degree nfj, and it's at least 1. Okay, so where has this gotten us? Since elements of I are finite sums of something in A times one of these elements, if we have some way of writing 1 as A1C1 plus 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 AMCM, each CJ is associated to some polynomial Fj. And one of the hard things to understand about this polynomial ring, this ideal, is that they're coming from infinitely many, there's contributions to this polynomial ring and this ideal from any non-constant monic polynomial in f bracket x. And for many, many choices of f, there's going to be a huge number of these polynomials. But now each CJ corresponds to one polynomial. So we're down to some special finite set of polynomials, f1 up through fm. And we know that, for example, there is a splitting field for the polynomial f1 of x over f, and there's a splitting field for f2 of x over f, and so on. we've talked mostly about splitting fields for one polynomial at a time, but there is a finite extension L of f in which each one of these polynomials splits completely together. So fj of x is a product from I equals 1 up to nfj of x minus rij in L bracket x. So we have one linear factor for each up to the degree. The number of linear factors is the degree. And one way to think about it is take a splitting field of f1, that's some field, say E1, and then take a splitting field for f2 over E1, and that's a finite extension of E1, and so on. And you can see that there's a finite extension in which all of these polynomials split completely together. Okay, so what are we going to do? The idea is that we're going to construct a ring homomorphism from this giant polynomial ring A to this finite extension L. And when, so over on the left here, this is something in A times something in I. These are all in A, certainly. So we can apply phi to the left-hand side of this equation. We can also apply phi to the right-hand side of this equation. And applying phi to this equation is going to give us a contradiction. So I'm going to pause and erase and then tell you how to define this ring homomorphism phi in such a way that shows that I is a proper ideal of A. Let's carry out this idea of constructing this special ring homomorphism from A to L. And A is some giant polynomial ring over F. So if we want to construct a ring homomorphism, we just need to say, how does this ring homomorphism act on F? And then what does it do to each of these generators? And then we can just extend it to a homomorphism. So what we're going to do is define phi so that it fixes F. So for example, it sends any element of F to itself. So it sends 1 to itself. And now we just have to say, what does it do to each of these T, F, I's? Well, if you pick one of the polynomials, Fj, so we have this special finite set of polynomials, F1 up through Fm. And if you pick one of the variables corresponding to one of these polynomials, it's going to send Tfj I to Rij. So if you pick one of these Fj's, you send the ith variable corresponding to Fj to this root Rij that comes from factoring Fj in L bracket x. And if you pick any other non-constant monic polynomial f that's not in that list, f1 up through fm, send all the variables corresponding to that polynomial to 0. Okay, so we've said what phi does to each of these generators of this polynomial ring. So this really does give a homomorphism from A to L. And we have seen that if you have a ring homomorphism from A to L, that you get a corresponding homomorphism from A bracket x to L bracket x by acting on the coefficients of these polynomials. So you send a polynomial in A bracket x to a corresponding polynomial in L bracket x by sending each coefficient to wherever phi sends it. So you have some coefficient in A, it goes to some coefficient in L. And now we're going to look at some particular special elements in A bracket x and see what phi does to them. Well, what do we know? We have these special elements of the form fj of x minus this big product x minus tfj comma I, where we go over the variables corresponding to this monic non-constant polynomial fj. And phi, well, phi sends a polynomial in f bracket x to itself. I mean, it doesn't change anything in f. So it sends, first, it sends the difference of these two polynomials to phi of the difference. It's a ring homomorphism. It sends fj of x to fj of x. Where does it send this? Well, it's straightforward to see that, I mean, it's a ring homomorphism. It's going to depend on where phi sends each of these tfj comma i's. And we know that it sends tfj comma I to rij. So this gets sent to this product from I equals 1 to nfj of x minus rij. But this is 0 in L bracket x because fj of x is this product. Okay, so now this is great because phi sends this whole polynomial to 0 in L bracket x. So in particular, it sends every coefficient of this polynomial to 0 in L. And what was Cj? Cj was some coefficients of this polynomial fj of x. We didn't specify which one, but this polynomial fj came from the fact that we knew Cj was some coefficient of a difference that looked like this. So we picked a polynomial fj of x of which one of the coefficients was Cj. And now we're in good shape because where does phi send a1c1 plus 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 amcm? Well, it sends a1c1 to phi of a1 times phi of c1. So if phi of cj is 0 for each j, the whole left-hand side gets sent to 0 plus 0 plus 0 plus 0. But the right-hand side gets sent to 1. So what is this saying? This is giving us 0 equals 1 in L bracket x, or 0 equals 1 in L. Right? I guess these are constants in L bracket x. So 0 equals 1 in L. And this is clearly a contradiction. So this is not possible. So the thing that we were contradicting was that we had some expression a1c1 plus 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 amcm equals 1. And this is kind of a tricky argument to remember how this works. The main idea is for each cj, there's some corresponding polynomial fj that you work with. And now you have some finite set of special polynomials, and you can take some special finite extension in which all of them factor into linear factors. There's one extra idea, which is now you want to come up with a special homomorphism from a bracket x to L bracket x. Okay. So where are we now? So I is a proper ideal of A, and we know that that means that it's contained in some maximal ideal. And this is the place where we have to apply Zorn's lemma to see that that's true, but this is something that we talked about in 206b. So let's name that maximal ideal. So I is contained in some maximal ideal. Let's call it M, maximal ideal of A. And now we know that A mod M is a field. And in fact, we're going to show that A mod M has a subfield isomorphic to A. So you can think of A mod M as, has a subfield isomorphic to F, the field that we started with. So we can think of A mod M as an extension of F. And we're going to show that it's an algebraic extension and that, in fact, it is an algebraic closure of F. So I'll pause and erase, and we'll do the rest of the proof. We have this huge polynomial ring A, and we found this special maximal ideal M inside of A. So A mod M is a field. So what do we know? We know that A is a polynomial ring over F. So there's this injective map from F into A. And we have this natural projection map from A to A mod M. So taking the composition, we get this map from F to A mod M. And it's a homomorphism between fields. So the kernel is either 0 or it's all of F. And it's easy to see that it's not all of F. So there's this injective map from F to this field, A mod M. So what does that mean? A mod M has a subfield isomorphic to F. So we can view A mod M as an extension of F. Okay, so what kind of extension is it? Our next goal is to show that it's an algebraic extension of F. All right, so let's take a non-constant monic polynomial f of x in F bracket x. And we know that each coefficient of this difference, f of x minus the product from I goes to 1 up to nf of x minus tfi, these variables corresponding to f, is in I. So they're definitely in M because I is in M. So when we take this thing that's in A bracket x and look at what happens when we send it to an element of A mod M bracket x, we get 0 because every coefficient here is in M. So what does that mean? That means that f of x equals the product from I equals 1 up to nf of x minus tfi bar in A mod M bracket X, where what is this TFI bar? Well, this is the image of TFI under this projection homomorphism from A to A mod M. It is TFI mod this maximal ideal M. So the important thing is that every polynomial, non-constant monic polynomial in F bracket X factors as a product of linear polynomials in A mod M bracket X. Okay. Well, what do we know? These TFI bars, these are algebraic over F. Why? Because the roots of polynomials in F bracket X. TFI bar is a root of F of X. So when we look over the collection of all of these elements, these are all algebraic. And we know that A is generated over F by these TFIs, this huge number of variables. You have some variables for each non-constant monic polynomial. So A is generated over F by all of these polynomials. And just thinking about how you go from a ring R to R mod I, if you have a generating set for A over F, you get a generating set for A mod M over F. This is generated by the images of these generators for A. So A mod M is generated over F by these TFI bars. So what's the point? Is that A mod M is generated over F by a collection of algebraic elements over F. So what does that mean? Well, we have proven that if you have two algebraic elements, alpha and beta, the sum, the difference, the product, the quotients of those elements are also algebraic over F. So what we're seeing is A mod M is an algebraic extension of F. All right, so what do we need for A mod M to be an algebraic closure of F? We have seen that it is an algebraic extension of F. We just need to see now that it's algebraically closed. So our goal is going to be to show that every monic irreducible polynomial in A mod M bracket X has a root in A mod M. Why irreducible? Well, if you show that every monic irreducible polynomial has a root, it's clear that every monic polynomial has a root in A mod M as well. Monic, you could always scale by the lead coefficient of your field. So it's enough to show that every monic irreducible polynomial in A mod M bracket X has a root in A mod M. And I'll pause and erase, and we'll prove this last piece of this long argument. Let's finish the proof. Let's say pi of x is a monic irreducible polynomial in A mod M bracket X. So we want to show that pi of x has a root in A mod M. And it's enough to show that pi of x divides some monic irreducible polynomial f of x in F bracket X. Because then we could think of f of x as an element in A mod M bracket X. And we've already seen that f of x splits completely as a polynomial in A mod M bracket X. So all of the roots of f of x are already in A mod M. So if pi of x divides f of x, then certainly the roots of pi of x, which are also roots of f of x, are already in A mod M. Okay, so here's the idea. We're going to focus on one root. Let's say there is a root alpha of pi of x in some finite extension of A mod M. So what does that mean? Okay, so this is a monic irreducible polynomial in A mod M that has alpha as a root. So it is the minimal polynomial of alpha over A mod M. All right, so this alpha is algebraic over A mod M. It's the root of a monic irreducible polynomial. And we know that A mod M is algebraic over F. We proved this before. So theorem 20, this thing about L is algebraic over K and K is algebraic over F, this tells us that alpha is algebraic over F. Okay, so this is great news because that means that there's some polynomial f of x in F bracket X that has alpha as a root because alpha is algebraic over F. But that means that f of x is some polynomial in a mod m bracket x that has alpha as a root. So the minimal polynomial of alpha over a mod m has to divide f of x. And that minimal polynomial is pi of x. So pi of x divides f of x. Each root of f of x is already in a mod m. So alpha is in a mod m. And we have seen that, okay, every monic irreducible polynomial in a mod m bracket x has a root in a mod m, which shows that every polynomial, every non-constant polynomial in a mod m bracket x has a root in a mod m. So a mod m is an algebraically closed field that is an algebraic extension of f. So it is an algebraic closure of f. Okay, so I do feel that this is one of the longest and most complicated arguments that we've seen so far in this course. I also want to point out that this is not the argument that's given in Dummett and Foote, section 13.4. This argument comes from Conrad's notes, constructing algebraic closures. The Dummett and Foote argument maybe is a little easier. But on the other hand, in this argument, we have actually seen which field is the algebraic closure of f. It is this field, a mod m, that we described this giant polynomial ring. We found this ideal I in it. We applied Zorn's lemma to see that there's a maximal ideal m containing that ideal I. And then we saw that a mod m was an algebraic closure of f. The Dummett and Foote argument is a little easier, but it doesn't make it so clear what exactly the algebraic closure of f is. It's just saying that there is one. So I encourage you to go and look at this other argument and see how it compares. Conrad also writes a little bit about the comparison between these two arguments in his notes. Okay, so I'll pause and erase and just talk about some final things related to algebraic closures. Let's prove one more quick result about algebraically closed fields. This is proposition 31 in section 13.4 of Dummett and Foote. Let K be an algebraically closed field and let F be a subfield of K. Then the set of elements F bar of K that are algebraic over F is an algebraic closure of F. Okay, so K is this huge algebraically closed field. Maybe it contains some elements that are not algebraic over F. But if you just look at the subset of elements of K that are algebraic over F, that's an algebraic closure of F. Okay, so by definition, F bar is an algebraic extension of F. It's a collection of all of these elements in this field that are algebraic over K. We know that you can add, multiply, divide, and you're going to get more elements of K that are algebraic over F. And everything in this field extension is going to be algebraic over F. So this is an algebraic extension. And we know that if you take a polynomial in F bracket X, it splits completely in K bracket X. Because, everything in K bracket X splits completely. It's algebraically closed. So what does it look like? Maybe it's not monic, so it has some lead coefficient that's in F times a product from I equals 1 up to its degree, whatever it is, of x minus alpha I, a bunch of linear factors. So what we want to do is show that every polynomial f of x in F bracket X already splits completely in F bar. So we want to look at the coefficients of this polynomial and see that they're all in F bar, that this really is already how f of x factors in F bar bracket X. And what do we know? Every root alpha I of f of x is algebraic over F. Why? It's a root of a polynomial in F bracket X. It's definitely algebraic. So it's in F bar, because this is all the elements that are algebraic over F. So we have all these linear factors, x minus alpha I. And the coefficients here are certainly in F bar. It's 1 times something in F bar. So if we take the product of this whole bunch of linear polynomials in F bar bracket X, we're getting another polynomial in F bar bracket X like in f bar bracket x, f of x already factors as some constant that's in f times these linear factors, each of which is in f bar bracket x. Okay, so what have we seen? That f bar is an algebraic extension of f in which every polynomial in f bracket x splits completely. So f bar is an algebraic closure of f. Okay, so Dummin and Foote present proposition 31 as having two parts. And the second part is that all algebraic closures of a field f are isomorphic. They don't give the details of the arguments. They instead say that it's similar to the proof that any two splitting fields for f of x over f are isomorphic. It is similar. It's not so easy to write down all of the details. If you want to see the details, Conrad gives a full proof of this in his notes on Zorn's lemma and some applications too. I'll put a link in the course website. This is corollary 1.3. So I'm not going to present the proof of this here, but I encourage you to check it out and think about it. So I just want to end this lecture with a quick discussion of something that goes back a few lectures now. The fundamental theorem of algebra says that C is algebraically closed. I've mentioned this before, but we're not going to prove it yet. We'll prove it later in the course. What's one thing that this means? If you have any polynomial with coefficients in C, a non-constant polynomial, then it has a root in C. So if you have any polynomial with coefficients in a subfield of C, like Q or R, it has a root in C. And more than that, I mean, it splits completely into a product of linear factors in C bracket x. Okay, well, C is an algebraically closed field, and it has a lot of subfields. One thing that we see from this is that an algebraically closed field contains an algebraic closure of any of its subfields. So in particular, C contains an algebraic closure of any of its subfields, like C contains an algebraic closure of R, C contains an algebraic closure of Q. What is it? If you take K equals the complex number C, F equals Q, then the set of all elements Q bar of C that are algebraic over Q is an algebraic closure of Q. But we already talked about that a few lectures ago. That is this field Q bar, the set of all elements in C that are algebraic over Q. And now we can see that this is an algebraic closure of Q. Now, we haven't completely proven this yet because this relies on the fact that C is algebraically closed, but we'll get there a little later.